Good morning, dear students. Today we are going to study the second part of the periodic table. Yesterday we have studied Daubigne's law of triads, Newland's law of octave, Mendeleev's periodic law and Moseley's periodic law. The content for today's part is modern periodic table, in which we are going to study periods groups. In groups, we are going to study group 1, group 2, group 3 to 12, group 13 to 16, group 17, group 18, electronegativity, metals, non-metals and allotropy. Now this is periodic table. Periodic table consists of groups and periods. Now horizontal rows, as we move from left to right, are called as periods. There are total 7 periods. So, period 1 to period 7. Now, period number is equal to number of shells. Now, in case of hydrogen, the atomic number is 1, so it consists of only one shell and it is placed in period 1. Lithium consists of 2 and 1 as its electronic configuration. It consists of 2 shells, so it is placed in period 2. In case of sodium, atomic number is 11, 281. So, it consists of 3 shells, and so it is placed in period 3 and so on. So period number is equal to number of shells. In case of lithium, we can see that the electronic configuration is 2, 1, in beryllium 2, 2, in boron 2, 3 and so on. In case of neon, it's 2, 8. So it starts with 1 electron entering shell and ends with 8 electrons, so that its outermost shell is complete. Yes, and it follows octet rule. Now number of valence electron increases by 1. Here you can see, in case of sodium also it's 281, magnesium 282, aluminium 283 and so on. So number of valence electron increases by 1. Valence electron are the electron present in the outermost shell. The valency also keeps on changing for period 2 and 3. Now in period 1, there are 2 elements, hydrogen and helium. In period 2 and 3, there are 8 elements. In period 4 and 5, there are 18 elements. And in period 6, there are 32 elements. So horizontal rows are called periods. There are 7 periods. Period number is equal to number of shells. Number of valence electron increases by 1. Valency changes in period 2 and 3. Now students, we have studied the periods. Now let us understand about the groups. Now what are groups? The vertical columns as we go from top to bottom are called as groups. There are 18 groups. Group 3 to 12 you don't have to study. Now let us understand about the groups. So vertical columns are called as groups and there are 18 groups. Group number is equal to number of valence electron. For example, group 1 consists of 1 valence electron, group 2 consists of 2 valence electron, group 3 consists of 3 valence electron, group 4 consists of 4 valence electron, group 5 consists of 5 valence electron, group 6 consists of 6 valence electron, group 7 consists of 7 valence electron, and group 8 consists of 8 valence electrons. Now, in a group, the valency remains same. For example, hydrogen, it's 1. For lithium, it's 2, 1, that is 1 is the valency. For sodium also, the valency is 1. so valency remains the same, but the valence electron changes. For example, in case of lithium, it's 1, beryllium 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, neon 8. So vertical columns are called groups. There are 18 groups. Group number is equal to number of valence electron. Number of valence electron changes, but valency remains same. So this is all about groups. Now children, let us understand the groups in detail. Let us see group 1A. Group 1A consists of elements like lithium, sodium, potassium, rubidium, cesium and francium. They are called as alkali metals. The valency is 1, that means they are univalent. They undergo oxidation. They are good reducing agents. They are electropositive. Being metal, it loses electrons, so it is electropositive, and it is highly reactive. So group 1 elements are lithium, sodium, potassium, rubidium, cesium, francium. They are called as alkali metals. They are univalent. They undergo oxidation. They are electropositive. They are highly reactive, and they react with water to form strong alkali. For example, sodium reacts with water to form sodium hydroxide, which is a strong alkali. Now let us understand about group 2. Now group 2, it consists of beryllium, magnesium, calcium, strontium, barium and radium. They are also called as alkaline earth metals. Their valency is 2, that means they are bivalent, and they have properties similar to alkali metals. So this is all about group 1 and group 2. Group 3 to 12 you are not supposed to study. So you have to remember the names of the elements present in different groups.
Elements are arranged in the increasing order of atomic numbers. Horizontal rows in the periodic table are called periods, and vertical columns in the table are called groups. Elements in the modern periodic table are arranged in 7 periods and 18 groups. You can locate an element in the periodic table by referring to the relevant period and group. For example, sodium belongs to the first group and the third period. You can observe trends in the properties of elements as you analyze them across periods and down groups. Let's look at the basic trends in belief. The properties of elements change gradually from left to right in a period, as an electron is added to the outermost shell. For example, sodium is highly reactive, and magnesium is less reactive as compared to sodium. There is a drastic shift in properties between the last element of a period and the first element in the next period. For example, neon is inert, whereas sodium is highly reactive. Elements in a group display similar properties because they have the same number of electrons in the outer shell. For example, sodium in period 3 and potassium in period 4 belong to group 1. Both these elements are highly reactive and metallic in nature. Elements are placed in periods based on the number of shells in their atoms. That is, the number of shells in the atoms of all elements in a period is the same. While moving from left to right in a period, the atomic number increases by 1 unit at each step. This means that a valent shell electron is added to the atom. Consider the example of the elements in period 3, which have 3 shells, K, L, and M. The third shell starts getting filled as we move from left to right in the period. Thus, the first element in this period, sodium, has 1 electron in its valence shell, while the last element, argon, has 8 electrons in its valence shell. Let's take a look at the basic characteristics of each period in the table. The first period is the shortest period and contains only 2 elements, hydrogen and helium. The second period contains 8 elements, from lithium to neon. The third period also contains 8 elements, from sodium to argon. The fourth period is a long period and contains 18 elements, ranging from potassium to krypton. The fifth period contains 18 elements, starting from rubidium and ending at xenon. The sixth period contains 32 elements, from cesium to radon, which also includes 14 lanthanides, from cerium to lutetium. The seventh period is incomplete at present and can accommodate 32 elements, which includes 14 actinides, from thorium to lawrencium. It will be filled up as new elements get discovered, as is expected. In addition to the 7 periods across, the periodic table is classified into 18 groups vertically. The classification in groups is based on the number of valence electrons in an atom. The number of valence electrons of elements down a group is the same. Therefore, the elements in a group show similar physical and chemical properties. Let's take a quick look at the properties of the elements in each group to examine their similarities. If you begin with group 1, this group has 7 elements: hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Elements in this group contain 1 valence electron. That is, their general outer electronic configuration is ns1. Because of their configuration, they enter into chemical reactions easily. That is, they are highly reactive. All these elements form basic oxides that react with water to form alkalis. So the elements of group 1 are also known as alkali metals. For example, sodium reacts with oxygen to form sodium oxide, which then dissolves in water to form sodium hydroxide. Let's now look at the elements in group 2. The elements of the second group are beryllium, magnesium, calcium, strontium, barium, and radium. These contain 2 electrons in the valence shell. That is, their general outer electronic configuration is ns2. These elements are also known as alkaline earth metals, since they hydrolyze easily to form alkaline solutions. For example, magnesium oxidizes to form magnesium oxide. This compound can be dissolved in water to form magnesium hydroxide.
Now let us study group 3 to 12. Group 3 to 12 is called as transition elements. All of them are metals. They are colored. Now this group you don't have for studies. This is just for your reference. It also consists of lanthanoids and actinides series. Lanthanoid group 3 and actinides group 3. Lanthanide is present in period 6 and actinide is present in group 7, and these are called as inner transition elements. So group 3 to 12 are transition elements. They are all metals, they are colored, they are chemically reactive, they lie at the center of the periodic table. Lanthanides are called as rare earth, actinides are called as radioactive. But this group you don't have to study. This is just for your reference. Group 13 to 16 are called as post-transition elements. It consists of metals, non-metals and metalloids. Metalloid shows property of both metals and non-metals. Now let us study the next group, that is group 17 or 7A. It consists of fluorine, chlorine, bromine, iodine and aspartame. Now these elements, this group has 7 valence electrons. They have valency 1, that means they are univalent. They undergo reduction. They are electronegative. They are highly reactive and they are good oxidizing agent. So group 17 elements present are fluorine, chlorine, bromine, iodine and aspartame. They are halogens. They have 1 valence. They are electronegative. They are highly reactive and they are good oxidizing agent. Now let us study the next group, that is group 18. It consists of helium, neon, argon, krypton, xenon and radon. They are also called as noble gases, inert gases or zero group elements. They do not lose or gain electron. Why? Because they are stable and that's why they don't form compounds. So this is all about group 18.
The next group is group 3. The elements in this group are boron, aluminium, gallium, indium, and thallium. Group 3 elements have 3 valence electrons. Hence, their general outer electronic configuration of atoms here is Ns2Np1. These elements form covalent compounds that are formed by mutual sharing of electrons. For example, boron trichloride is formed by the sharing of 3 electrons between boron and chlorine. Let's move to group 4. The elements in this group are carbon, silicon, germanium, tin, and lead. These elements contain 4 valence electrons and their general outer electronic configuration is Ns2Np2. The elements in this group combine with halogens to form the respective halides. For example, carbon combines with chlorine to form carbon tetrachloride. In the same way, silicon combines with chlorine to form silicon tetrachloride. Next is group 5. The elements in group 5 of the periodic table are nitrogen, phosphorus, arsenic, antimony, and bismuth. These elements contain 5 valence electrons and hence their general outer electronic configuration is Ns2Np3. These elements react with hydrogen to form hydrides. For example, nitrogen combines with hydrogen to form ammonia gas. Similarly, arsenic combines with hydrogen to form arsine. Let's now consider group 6. The elements of group 6 are oxygen, sulfur, selenium, tellurium, and polonium. These elements contain 6 valence electrons and hence their general outer electronic configuration is Ns2Np4. These elements react with hydrogen to form hydrides. For example, water and hydrogen sulfide. Group 7, The group of halogens is next. The elements of group 7 are fluorine, chlorine, bromine, iodine, and astatine. They contain 7 valence electrons, and hence their general outer electronic configuration is Ns2np5. The elements in this group are also known as halogens because they have originated from the sea. These elements have the tendency to gain electrons and become stable. This property helps in the formation of compounds with alkali metals. For example, chlorine accepts 1 electron from sodium to form sodium chloride. The last group is group 8, or the zero group. The elements in this group are helium, neon, argon, krypton, xenon, and radon. All these gases, except helium, have highly stable Ns2np6 electronic configuration in their outer shell. Helium has 1s2 configuration. They are also known as inert gases because they don't react with other elements.
Now let us study about the periodic property, that is electronegativity. Yesterday we have studied electron affinity, ionization potential, and atomic weightage. Now what is this electronegativity? In simple words, it means greedy element. Now, electronegativity, they accept electrons or electron pair. For example, you can see here chlorine molecule. Now, a bond has how many electrons? There are 2 electrons between a bond. Now, in case of HCl, chlorine is more electronegative than hydrogen. So instead of breaking the bond, chlorine will pull the electron towards itself. So this tendency of an atom to attract electron towards itself when combined in a compound is called electronegativity. And we have seen 2 examples, chlorine molecule and HCl. Now let us see about the metals. As you all know that metals, they lose electrons, they undergo oxidation, they are good reducing agents, they have low electronegativity. Just now we have seen what is electronegativity, tendency to attract electron towards itself. They have low electronegativity, metallic character decreases across the period, and metallic character increases down the group. So this is about the metals.
Electronegativity. When 2 different atoms in a molecule are bonded together by a covalent bond, the electron pair forming the bond is not shared equally by both the atoms. In other words, the shared pair of electrons do not lie in the middle of the molecules, but shift towards the atom having greater electron affinity. The tendency of an atom to attract electrons to itself when combined in a compound is called electronegativity. For example, in the molecule of hydrogen chloride, electron pair is attracted more towards chlorine. Thus, chlorine is more electronegative than hydrogen. The value of electronegativity depends upon the ionization potential and electron affinity of the atom. In a polar covalent bond, the shared pair of electrons is attracted by one of the atoms, giving partial positive and negative charges to the 2 atoms. Small atoms attract electrons more than the large ones and are therefore more electronegative. Low electronegativity is the characteristic of metals and high electronegativity is the characteristic of non-metals. Electronegativity increases in going from left to right across the period because atomic size decreases from left to right. In a group, atomic size increases, hence electronegativity decreases.
Now let us study non-metals. Non-metals, as you all know, they gain electrons. They undergo reduction. They are good oxidizing agents. They have high electronegativity. Non-metallic character increases across the period as we go from left to right, and non-metallic character decreases down the road. So this is all about non-metals. Now let us study about allotropy. The ability of an element to exist more than one form is called allotropy. It is exhibited by the elements of group 14. For example, carbon has exist in different allotropes except for lead. Group 15 also show allotropy except for bismuth, and group 16 also show allotropy. So this was all about allotropy.